Alright, welcome back. We're talking about radioactivity, and we talked about three types. We have alpha, beta, and gamma radiation. And it said, say we had three rocks, and one was emitting alpha radiation, one was giving off beta particles, and the last one was giving off gamma radiation. And you were allowed to throw one of them away, get rid of it. One of them you had to hold in your hand, and the other one you had to put in your pocket. What would be the proper way to do that? Okay, think about that for a second. You can pause it if you'd like, and then we'll answer it. Alright, now that you've stopped and thought about it for quite a while, I'm sure puzzled it for 30-40 minutes before you turn this back on. Here we go. If you were going to throw one away, the obvious one to throw away would be the gamma emitter, because gamma rays are extremely dangerous, high energy, and there's just no way to safely contain those. The one you could hold in your hand would probably be the alpha particle, because they're very large, and they're positive. They can't go in. You'd be protected by the surface of your skin. And to put in your pocket would be the beta particles, or electrons, because they would be stopped by the clothing in your pocket, and so it would keep you from being exposed to it. So that would probably be the correct way to do that. Hopefully you made the right choice and you're not becoming a mutant even as we speak, because once again, usually when there's mutations, they tend not to turn you into the X-Men or the Incredible Hulk or whatever. They just tend to kill you or do bad things to your cells and do damage. Alright, so you're less better off than you were before. Alright, so we're talking a little bit about environmental radiation. Just keep in mind, once again, radiation is always there. Well, we have natural or environmental or background radiation. It's just what occurs naturally, and some of that comes from rocks and stuff that are radioactive. Technically, people who live in brick houses or stone houses are probably exposed to a little bit higher levels of radiation, because some of the minerals used to make the bricks and stones that their houses are built out of would contain probably some kind of uranium, some atoms of uranium in there, and there's some radiation being released from that, versus if you lived in a completely wood-built house. But no, that doesn't mean go sell your house if it's made out of bricks. It's just saying that there's a slightly higher radiation there, because minerals contain uranium. Radon is a gas that's released. We'll talk about the breakdown of uranium in a little bit. And as it's released from rocks that contain uranium, it can seep up. It's a gas, and colorless gas, and it will seep up from the ground. So a lot of people have basements. If they're in areas that have larger uranium deposits, it could build up in those basements if they're not well ventilated or something like that. And so there's a possibility that, and it can be a problem. And so there are radon detectors that you can buy and put in your house. And so, and once again, if you're exposed to large amounts of it, then once again that can be a very serious problem. Okay. Even in the human body, we have potassium 40, which is a radioactive form or isotope of potassium, which is a essential element. But a certain amount of the potassium in our body is potassium 40, and it breaks down and gives off small amounts of radiation also. Okay, so about 80% of what we're exposed to just comes from our environment, and we can't really escape that by doing anything. We can take measures to protect ourselves, like if we had the basements and areas that seem to build up radon, then we would need to do something about that. Other sources are man-made, for example, medical, X-rays, radiation treatments, things like that. Possible smoke detectors, for example, use radioactive elements. I believe it's americanium, which has a little piece of a radioactive element in there that secretes a stream of particles going across. If something interferes with that stream of particles, such as smoke, okay, for example, then it sets off an alarm, and basically that's what a smoke detector and so forth, things like that, how those work. There is fallout from nuclear tests that are done around the world. North Korea and the United States and various people do testing on nuclear weapons, so there is some of that. There is, if you're near Chernobyl or Japan or Three Mile Island where there's been a nuclear accident, there's going to be a certain amount of radiation released from that. But generally, most of the nuclear waste in a normally functioning nuclear reactor is contained and is buried and isolated, so you're not actually being exposed to that. In fact, actually coal plants, as they burn coal, which has usually contains elements and minerals in it that contain both thorium and uranium. Thorium is one of the byproducts as uranium breaks down. And when they burn coal, that releases the radiation from those elements that are in the coal deposits that they're burning. And so actually that released a fair amount of radiation into the atmosphere. So actually burning coal can also release radiation, even though not directly as a nuclear power plant would. But just to keep in mind, there is no simple solution, no one way of power source that does not have some drawbacks and problems with it. All right. Now, the radiation, most of it is fairly harmless. It probably doesn't do a lot of damage, but some of it, especially gamma radiation, can do damage to our cells. Like I said, can cause mutations. Those mutations may be fairly minor, just a few cells. But if those mutations were in sperm or egg cells, then that could either cause difficulty in someone becoming pregnant by sterilizing those cells, or just causing mutations in the offspring that could be passed on. More commonly is that it may cause mutations in the cell division part of the DNA that controls cell division, and you have rampant cell division, which is basically what cancer is. Not all cancer is caused by radiation, but radiation is one of the things that can cause cancer. So that's also a possibility. Now, kind of an interesting thing is one of the first things that people started doing with chemistry were alchemists back in the early beginnings of what we call chemistry. Now, really, the only people doing that were alchemists, and alchemists were basically trying to find what they call the philosopher's stone, or some magic way that they could change one element into a different element. The idea is you take something like lead, which is heavy and dense, and change it into, say, gold, which is also heavy and dense, and they were always looking for ways to change base metals such as lead, mercury, and so forth into valuable metals like gold and silver for obvious reasons. And they were largely unsuccessful, but a lot of what they used while they were trying to do that was used by early chemists to start learning what we know about the chemical world. Okay, but interesting enough, we can do that. It's called transmutation, and one element can change into another. And part of that happens when, for example, uranium breaks down. It changes into actually a large variety of elements on its way down. A lot of it will eventually become lead, but it will change through a lot of elements on the way down. And so one element can be changed into another. Now, normally we said if an element has a certain number of protons, it is that element, and it will be that element, okay? And it will be, as long as it has that number of protons. But if something happens to change the number of protons, then you can actually change one element into another. Now someone says, well, why haven't people, for example, changed lead into gold? Well, the problem is it's easier to do with some elements than others. Unstable ones, such as uranium, will do it and can be encouraged to do it. Others, it would be very difficult because they have very strong forces holding them together. And the costs and expenses of it would not be worth the output of the small amount of gold and so forth that you might produce from it. So no, we're still not getting rich from that, and no one's going to just all of a sudden start changing lead into gold and become multimillionaire. Sorry about that to crush your dreams, but there we go. Let's look at how transmutation works in the most common natural way for it to occur on its own, and that is when we have the breakdown of a radioactive element such as uranium. Now, if you remember, in the uranium atom you have a bunch of protons and neutrons, okay? And the protons want to repel each other. That's the electrical force that they want to repel each other and go flying off in all directions. But there's a strong nuclear force that the neutrons help to hold them together. And most of the time, the nuclear force is the stronger force, and it holds it together quite well. But as you get into large atoms, such as uranium, which is element number 92, something there's 92 protons, and something like 146 or so neutrons, it begins to get a little unwieldy, and it's kind of hard to hold it together, and therefore we say it's more unstable. Now, some uranium atoms, such as uranium-235, is fairly stable, and they do not react or break down. But uranium-238 is the one that we usually use when we talk about nuclear power plants and things like that, because it is, that combination of protons and neutrons is very unstable. Okay. Now, as it happens, we're going to look at this chart over here. This represents the atomic mass. In other words, the nucleons, how many protons and neutrons are in the atom. Uranium-238 has 238 of those, 92 of those are protons. So if you do your subtractions, that means 146 of those are neutrons. So there's a lot of neutrons, a lot of protons, and it's fairly unstable with that combination. Okay. Now what would happen is the uranium, if something triggers it, and we'll talk more about that later, usually a neutron smashing into it, but if a neutron smashes into it, it will begin to break down, and it will break down and it will give off a beta particle, alpha particle, which is basically the helium nucleus, which is 2 protons and 2 neutrons. Now if it does that, the atomic number now changes, a mass number, changes from uranium-238. It loses 4 AMUs, or 2 protons, 2 neutrons, so a total of 4 AMUs, to this helium atom that comes off, or helium nucleus. And that means instead of, since it loses 2, that means the atomic number goes down 2 to 90, which produces an element called thorium, named after, yes, you guessed it, Thor. Okay, the Norse god Thor. Okay, thorium. And it has an atomic mass of 234 because it's lost 4 nucleons, or protons, 2 protons, 2 neutrons. Okay, so it's 234. It only went down, the atomic number only went down 2 because that's 2 protons less than it had. Okay, now, so when it does that, now you have thorium-234. The helium goes off, eventually would hit something and gain some electrons and would become helium gas that we talked about before. It gets trapped underground. Now the next thing that can happen is then the thorium, okay, is going to undergo a breakdown too, and this time it's going to give off a beta particle, which would be an electron. Okay, now where does the electron come from? All right, well, basically one of these neutrons, which we said before, is going to give off the electron. Okay, so that's where the electron comes from. The neutron that gave off the electron now becomes a proton. So the when you have beta radiation, it basically increases the number of protons by 1, and it goes from thorium to proactinium, or Pa, which is the next one on the periodic table. Okay, and it gives off an electron, okay, or beta particle that goes off, and once again can do damage until it can enter the surface of something, and then eventually will be absorbed as an electron into that organism. All right, now the next one, proactinium, would also undergo basically where it gives off a beta particle, okay, and so it would break down and it would break back into, look at that, it gains a proton, so it's back to uranium. But this is uranium-234 because it's lost the protons from up here. So now we have uranium-234, so we're actually back to a uranium atom. Okay, and this uranium atom would lose a beta particle, which means you lose 2 protons, okay, and you lose 4 AMUs, or 4 atomic mass units, and it would become element thorium-230. Okay, then it undergoes beta radiation again, alpha radiation again, and it would break down into radium. Okay, we've heard of radium. All right, then it breaks down into radon. That's the clear poisonous gas we said that can sometimes build up from this breaking down. Okay, it can change into polonium. All right, now notice that polonium has 2 choices. It can either give off an electron and move up to actinium, or it can go straight and do another alpha radiation and go down into lead. Okay, then lead can change, give off an electron and have a neutron change to a proton, become bismuth, and it can go back to polonium, or then it can go down here and thallium, lead, bismuth, or polonium, and eventually going to end up as thallium or lead down here at the bottom. And that's why we talk about lead usually as being the end product of uranium transformation or changing down. So just a series of events, and this would have to happen over a long period of time for it to eventually go from uranium and eventually would become lead. If it becomes thallium, eventually thallium would undergo where a neutron changes to an electron, gives off an electron and changes to a proton and becomes lead. So lead is the final product of uranium breakdown. All right. Now, each time these happen, then there are different amounts of radiation given off. Either there's electrons, beta particles, or alpha particles, and also gamma radiation. intermediate product would be radioactive. That's why they continue to break down. Whereas lead, the final product here, would be a stable element.